discussing analysis and design phase of system dynamics modeling methodology. We talked about these fundamental notions, the different aspects of analysis and design. And then we talked about the various uses of sensitivity analysis and different types of sensitivity. Okay? Now, then we started talking about, we discussed those issues, the issues on the previous slide, the types, the uses or the types of sensitivity analysis. And then we started talking about various tools of sensitivity analysis, or for sensitivity analysis. Now, I will come back to analytical at the end. Let me start with simulation experiments. Well, as I said, there are two broad ways of doing it. One is just experimenting with the model so as to reveal the sensitivity characteristics of the various measures of the output to different parameters or structures or functions. The other one is deriving that sensitivity mathematically by this definition and analytically evaluating this expression, which requires that we have functions for all as a function of p, then we can do all that. Now, so we talk about that. That can only be done in linear systems, it turns out, in general. And then experimental design is it's not a third way, but really the third item is this sort of continuation of two. It's a systematic, structured, efficient, and scientific way of carrying out experiments. In our case, it will be in the context of simulation experiments rather than actual physical or laboratory experiments. Now, so when you start doing simulation experiments, one is simple enumeration of all possible, trying out of all possible values that you are interested in for all possible parameters. That is a name that's called sometimes full factorial design, because in the expression you have to get factorial. But before I talk about that, let me just say a few words about why full factorial is desirable. It can be done to a simpler approach, which says perhaps one value at a time approach. If you read this, if you have p parameters and you try each with 3 values, let us say you have 5 parameters and each you want to try with 3 typical values. A high value, a low value, and a medium value. Well, perhaps let us say one value at a time approach, the simplest, non-exhaustive approach would be you take each parameter and you take the parameter value to high and low and middle, and then you leave it at the middle, and then you take the next parameter, you take it to high and low, and then bring it back to the middle, then you take it. Well, that one, of course, will deal with, if you have p parameters, it will come up with 3p experiments, because with each you are doing 3 experiments, that is 3p experiments, which is doable, right? So non-exhaustive, not combinatorial. It's just, if you have 30 experiments. And you understand what the problem there is, though. You are not able to investigate at all the interactions between these parameter values. It's very likely that different combinations, interactions at different values will yield significant results, whereas if you leave, for every experiment, if you leave all the others at their middle values, base values, you may not catch those sensitivities. So, but sometimes if you have to do it, you can do that. That's still better than nothing, right? This is the simplest approach to simulation experiments and sensitivity analysis. For obvious reasons, people said this is not quite comprehensive and reliable. They said you need to try each parameter level at different combinations of all other parameter levels, right? Of course, then the game changes drastically. So that's what we call full factorial design. If we have p parameters, that has a name in experimental design, full factorial, we have p parameters and each tried at L levels, then you can show that you would have L to the p experiments needed. Suddenly it's a terrible number compared to 3p, right? So now it becomes a combinatorial problem, and immediately you get you hit millions, right? I mean, it is, if you have 3 levels, typically it's 3 levels, right? Typical L value is 3 levels. You can have more sometimes, but typically it's 3. Yeah, a high, a low, and a middle. So you kind of feel the response surface of function. That's 3 levels, which is typical. So if you have 10, then you get 3 to the 10. And this is, of course, for a small size model, right? 10 parameters is for a small size model. 10 parameters means you probably have a 3-stop model, which is a very small size model. All right. So, furthermore, this 3 to the 10 assumes that you have no replications. In other words, you are not investigating the error term, because to investigate really each experimental cell, if you want to do full statistical analysis, must also be replicated for, let us say, 3 or 4 times. So in each condition, you must run 3 or 4 random experiments, right? To have perhaps the most desirable data set for experimental design, also to analyze the error term, the normality error, so forth. You have to do the applications, and when you do the application, you have even more than 3 to 10. So immediately it becomes an impossible problem. It's a desirable, ideal, yet practically impossible experimental design, right? So when do you use full factorial design? You use it when you have a very small model, or when you have a model that you somehow convinced yourself, not perhaps either mathematically proven or not mathematically proven perhaps, but somehow by other ways, by logical or other ways, shown that you only need to analyze 5, 6 parameter values. You see? Then this becomes, of course, a very desirable experimental design. If you only have 5, 6 parameter values, you should use full factorial design, because then you get complete coverage of the entire experimental space. But that's pretty much the only place where you can use full factorial design. So this we may use as a sometimes called brute force approach, trying out all the combinations of all parameters, or we can statistics for full factorial design. Now, for this combinatorial and exhaustive nature of the and prohibitive nature of number of experiments needed, statisticians came up with the notion of fractional factorial design, using there is a good, very solid theory behind fractional factorial design. The idea is, under certain assumptions, you can prove that you can sample, and under certain assumptions, get a pretty good idea about the shape of the response function of this experimental surface, of the experimental response function, by not carrying out full factorial experiments, but a fraction of those only. And by fraction, it may mean only 10% of full factorial. I mean, we really mean a fraction, not 50%. It's a drastic, maybe a drastic reduction. So only a small fraction of those terms, in other words, instead of having 100,000, you may go down to 10,000 or 1,000, which is, of course, a significant reduction. Experiments. Now, fractional factorial makes some assumptions and eliminates all higher term interactions. Now, if you remember, you should remember, you're not going to get as detailed as you should know all this, of course, from experimental design courses. If you remember, some of the simplest interaction term is what's called a two-term interaction term, right? In other words, two at a time, when a value is taken high, and the other variable is at a lower or high value in pairs, when you take them, you wonder whether there's an interaction effect. But triple, or four-term or five-term interactions in theory can also be there, which is a very high-level, detailed interaction, we may call, which really causes this fractional factorial to yield huge numbers of required experiments. That's what really does it, these higher term interactions. So you say, beyond, let us say, triple, sometimes double or triple term interactions, you ignore all interaction effects. If you have 10 variables, you only consider two-term interactions, or at most, let's say, triple interactions. Then there is significant reductions in number of desired experiments. The systematic way of writing this down is in statistical design. It's called fractional factorial design, sometimes called orthogonal design. It's obtained by this, with the assumption of these orthogonal arrays when you write down your vectors, your design vectors, and which yields essentially to a significant reduction in number of desired experiments. The bottom line is, when you use fractional factorial design, know that you make certain assumptions. You must convince yourself that either higher term interactions don't exist, or if even they existed, they can be neglected, they are not strong, or you know that the results that you obtain are tentative. They are based on assuming that, after assuming that these interaction effects have been ignored. So you should keep that in mind when you do this type of experiment. And then you have a much smaller, let us say, instead of having a full coverage of the entire experimental space, you really have a kind of a sample, and this sample is based on this assumption. All right? Is on thinking that you are only sampling from the points that you believe are likely to be most significant, which are main effects, single main effects of each term, or two-term, three-term interaction effects, and that's. So, if you ever try that, in your work, in scientific analysis, or you do research on this, this is the starting point. Now, there are other ways of reducing experimental number of required experiments. One of them, I've skipped Taguchi now, one of them is random sampling. These are more classical than Taguchi. I mentioned this the last. Random sampling is another one. In a nutshell, there are different ways of doing random sampling, but in a nutshell, random sampling, but in a nutshell, it is just common sense. You can guess what it is. Assume that the full factorial experiments has, as I said, 100,000 required experiments. And assume that you identify them, all right? And then what you basically do, you just put them in some sort of geographic or geometric space in your conceptually somewhere. And then you create some random numbers, right? And depending on where the random number hits in this n-dimensional space, you just pick that experiment. And you say, and you decide how many you're going to pick, right? You say that depends on the economy of the problem. You say, I'm going to only carry out 1,000 experiments to 1,000 samples that I believe will be lucky enough to provide a good sample, random sample from this population. That makes sense, right? After all, don't you sample populations to decide, who votes what? And of course, that has stratified sampling, that's another strategy. But in general, you can take a sample and hope that the random sample will give you a good enough information about the characteristics of this function, of this response function. Now, the critical thing is what? Of course, the larger your sample, the more information you get, and the more random the stronger and healthier is the randomness of your sampling. Once again, the better result you obtain. But this, of course, assumes that you have no information about what? The shape of this function that you are sampling, because otherwise it would be stupid to randomly sample. Don't you agree? Because if you believe for some reason that this function is, you are looking for sensitivity and the function is kind of like this, and it doesn't make sense to sample randomly from everywhere, many of the points that you are sampling have no useful clues about this. So this assumes that we have no prior information, then random sampling is meaningful. So it's a sort of, again, a little naive approach. If you know nothing else, you do random sampling. And once again, if you are required, if full factorial says 100,000 experiments, what? You take a 10% sample? Still not small enough, right? You go down to 10,000. So maybe you take a 1% random sample, then 1,000, but then now you start believing that what? This 1% may not be quite representative. You might not be that lucky, so on. So this is again something that sometimes is introductory, it's naive and rarely used. The more advanced version, more popular version of sampling is Latin hypercube sampling, or it's some sort of stratified sampling. That is, it's not quite random. It is random in some sense, but in a stratified sense, it has certain logic. It's not purely random. Each parameter range is divided into n strata. That's called strata, just n points. So let us say each parameter has 10 different values. All right? We assign 10 different values to each parameter. And then for each parameter, you randomly pick one value. Right? So this is parameter 1. And it has these values. Here it has 5 values. Okay, so one of these. Then you have parameter 2. This has 5 values. So this is the value. Each interval is a value of the parameter. All right. So P3. And let us see P and PK. All right. Now, the way you end, so this is n of these, 1, 2, n. So what you do then is, here is 5. You come here and you say, you randomly pick, but you randomly pick a value from this parameter, right? Say randomly you get this one. And then you throw another dice. And they give me another one from here. right? And then say, give me another one. The next one may be here by chance, or it may not be there. And then the next one may be here. And the next one may be here. Then the next one may be here. Right? So you take one random value from each. Alright? This is one run. Okay? And then you run this, and then you do another one. Alright? So this is one experimental run, and then you go back and you say, let's try again. So you take another random number, another one from here, another one from here, another one. In a sense, you do this typically without replacement, so to speak, so that you never try. You kill this one, this particular path. You never, so that by chance you don't want to try the same again. So in that sense, without replacement. So you extinguish this possibility, and then you try again in case that one comes. That's non-existent for you. And then you try again. And the next time you may get something like this, right? And then you may get the same thing. You never know that. And then you get this, and then you get this, and then you get this. So here's another one. Another path, another experiment. Well, you repeat this n times. This approach is very different than the others. You repeat this n times, and you come up with one run of Latin Hypercube sampling, one experiment. One of the properties of this Latin Hypercube sampling is that it assumes that you don't have too many parameters, but what's more important for you is the number of values you try. So the focus here is on what? Is more on the precision, coverage of what? Of the different values of the parameters, full sensitivity of each parameter. In other words, perhaps you may have 20, 50, 100 values of each parameter. Here, this n is more important rather than number of parameters. In other words, you can easily have here 10, 15, 20 parameters. That doesn't quite increase the number of experiments that you do. The focus is more on, once you take one parameter, you try to get a what? Sort of a full, detailed, fine and high resolution analysis of that parameter by having many values. Not here you don't do it 3 values or 4 values or 10 values. It's a big perhaps 50 values, so forth. So it's a somewhat different approach, but oftentimes it's known to work. Because you are doing this without